are full, everybody's going to want to fall asleep. Because that's exactly what I would do if I was at home right now. I would get done and go sit down and take a nap. But I want to tell you, I'm one of those people, I'm a technology geek anyway. I love technology. I don't know about you all. But I do want to know one thing. Do any of you teach map reading in school still? I know we've got GPS and all that kind of wonderful stuff. Please continue to do that. We put the GPS in to come here tonight, and it was funny because it brought us all the way down here, and we went right by this place. And we went down the road, and it said turn left, and we went back in this little subdivision, which had this little. And the funny part was it brings you all the way around, and then it says turn right on Francis Marion Road, and you come back and you come here. And we followed that. And I said, isn't that great? I still love technology for that.
I do too. I'm actually going to go look at that house that's for sale.
They're nice.
I'm actually kind of happy about it.
There's a historic house down that way. I think maybe that's going to make you buy that or something. I appreciate you being here. And I appreciate Justin. I appreciate Natasha. We want to thank you and thank all of you for being here. I was afraid there was going to be like 3 teachers or something show up tonight. But I don't mind. I can talk to anybody, and my wife can tell you that I have no trouble talking whatsoever. I do want to ask, first of all, how many, from where you're at in school, high school teachers? Who are high school teachers? Okay. Middle school teachers. Any middle school teachers? Okay. Any elementary school teachers? Anybody I didn't know if that came in? Any secondary school teachers, college, and then Justin, you professor. Well, I appreciate all of you. The first part of what I want to talk about tonight has to do a little bit about me, but more about you. Okay? From a background standpoint, yes, I'm the engineering manager at Kaydon Bearings. We'll talk about Kaydon here in a little bit. And I'm born and raised in Ohio. Went to Fairfield Public Schools in Ohio, had the opportunity then to go to what was General Motors Institute up in Flint, Michigan. The water wasn't bad at that time, thank goodness. The rest of the city was because it was in the middle of a depression. And it was one of the hardest hit areas back in the early 80s. You may remember some of that. And got my bachelor's degree in mechanical engineering there. Got out of school and said, I don't think I'll ever go back to school again. And 10 years later, I went back to school and went to Xavier University and got my master's degree at that time. That gives you a little bit about my time in school. But what I want to talk to you about is some things about me, but it's about you and thanking you for who you are and for what you do. And to encourage you about some things that my teachers did that I know you do. I became an engineer because one day I walked into my high school counselor's office, and I said, what am I going to do in life? And he said, you're going to be an engineer. And I said, I am. He said, yeah. I said, what's an engineer? He said, well, that's somebody who does well in math and science. And I said, oh, okay. I said, so what do you do in engineering? He said, I don't know, but you use math and science and you're good at it, so you want to do that. I thought maybe I'd get a blow the whistle one day on the train. I didn't know. I never have seen the train yet. I've been doing engineering for over 27 years, and I still don't get to do that. But the things I did find was, I did have a love of math. I love math. I was one of those people, I just enjoyed it to death. I look back on it, I loved algebra. I loved geometry. That stuff in high school, I ate that stuff up. And the reason I ate that stuff up was because of the teacher I had. It wasn't born in me to just love algebra. Nobody just loves algebra. But I can still tell you this. Cop, colt, fad, then am I sad? Cop, colt, fad, then am I sad? Clear parentheses, combine of like terms, factor and distribute, isolate, addition, multiply, and subtract and divide. Mr. Chenoweth taught me that. My high school math teacher. He was also the one who worked us through geometry and helped me understand how to do proofs. I don't know if y'all still do proofs. One of those things I find I'm getting old, apparently. There's things that are different. My love of math, though, actually went all the way back to second grade when I really looked at it. And I tell you that because my teacher at that time, that was Mrs. Gibson. She taught us that we had games. I don't know if you're allowed to do that anymore. I liked it because I like winners and losers. I'm sorry, I'm not politically correct. And we used to have it where you'd line up at the back of the classroom, and then you'd run up to the chalkboard when we still had chalk, and you run up to the chalkboard, and she'd give you the thing and say, 7 plus 4, who can get it first? And I always wanted to win. I just love winning and doing that. That was one of those things that inspired me. It wasn't that the other kids were losers. Everybody won because you learned from that. And I really appreciated that. I appreciated the encouragement my teachers gave. That they were the ones who were trying to pick everybody up and helping us to make sure to learn and to do better. Science was great. I loved science. I liked all the different sciences we got to go through, and I was challenged by that. It's okay to challenge people. I really believe that. My challenge for me was physics. I got an opportunity to take physics in the 11th grade. In our system at that time, you had, I forget how they call it, semesters, but you had 3 quarters. But we had 4 different physics classes. So one semester, I was going to be cool. I doubled up. I took 2 physics classes, man. I thought I was something by doing that. But you know what it was? It's about taking a challenge and challenging students. I really believe that. I believe it's important to challenge people in life. One of the things I found is with the engineers I have a number of engineers that work for me, and I challenge them. I want them to grow as individuals and to continue to learn. We learn all through life. I learn something new every day. I learned once again, I'm not going to trust GPS to tell me exactly where I'm going to when I'm going someplace. But I want people to always grow and to learn and to do things differently. And that's what science, and that's what math, and that's what engineering and technology are all about. What is the next best way to do things? How can you do it better today than you did yesterday? I love industrial engineering. I had an opportunity when I worked for General Motors, back in the 80s and 90s. I, at one point, was the superintendent of industrial engineering. Man, efficiency. I love efficiency. I'm one of those people, I look at it in the morning and say, okay, now, here's how I'm going to do. I'm going to get up, I'm going to shave, and then I'm going to do this, I'm going to turn the water on, I'm going to do this so that I minimize the time it takes so I can maximize the amount of time I slept. Is what I'm really trying to do. I look at those kind of things from an efficiency standpoint. We challenge each other at work associated with how we do things from a manufacturing perspective to improve. That's what manufacturing is about, is how do you, first of all, we always look at safety. Safety is the most important thing. Quality comes next. How well you make things is paramount to what your customers get. Delivery. People want things on time. They want to make sure that, and cost. You want to make it at the minimum cost to maximize your profit. Some very basic things, but all of those things are very important to us. So, love of science, challenges, problem solving. This was the biggest scam that got pulled on me from high school. I remember back as a teacher say, because we all loved it whenever it was that straightforward, 7x plus 4a equals b and all that. And so you had to solve for, you solve for the equation. But then it would be, the train leaves California at 7 o'clock. And then there's a car that leaves New York at this time, and what's the guy's name who has the dog in the back seat kind of thing, It was the story problems. Everybody hated story problems. But story problems are life. And that's what engineering really is. It's all about solving the story problem. It's defining the story and then solving for it. Now, you'll eventually find you're going to get to that equation and put it in it, but it's about getting to that point of saying, here's what the problem is, here is what we need to look at for the variables to fix it. Your job is so important, and I appreciate it so very much for the next generation that's coming up. Our next generation needs you. They need you so badly to teach them and to encourage them and to lift them up. And I appreciate that. I want to talk for a little bit, real quick, about Kaydon itself. Kaydon, you're going to see this combination, you're going to wonder why SKF and Kaydon. SKF a couple years ago purchased Kaydon. Kaydon was a smaller company that was, and I'll talk a little bit about it, that came out of Michigan. But SKF is a large Swedish company. SKF stands for something, and I'm not even going to try to pronounce it because it's Swedish. And it's got all kinds of things that I wouldn't get right and would sound very bad. But it's a great company. It was founded in 1907, has 48,000 employees. This tells you a little bit about the sales. It's located, the headquarters in Gothenburg, Sweden. U.S. headquarters in Lansdale, Pennsylvania. There's 140 sites in 28 countries, 16 global technical centers. Technical centers are important in business. It's important that the engineers and the scientists continue to work to develop new and better. Our parent company of Kaydon Corporation. This shows a few of the applications of the bearings, and up in the right-hand corner, Sven Wingquist, the founder of SKF, inventor of the double-rolled self-aligning ball bearing. This tells you a little bit about net sales if you wanted to look at that kind of stuff, getting into where the market is. The point of this chart is to show how many different industrial areas that these bearings for SKF go into. Not only cars and light trucks, but aerospace, railway, off-highway trucks, two-wheelers, industrial and heavy equipment, energy, vehicle aftermarket, industrial distribution. This is a little bit about the sales by region. SKF, the point of this is SKF is a global company. Talk a little bit about Kaydon. Kaydon is the smaller part of SKF. SKF is the large, we consider ourselves, we make the niche of the niche bearings. We make bearings other people don't make. We make them, and they are very specific applications, and they go a little bit differently than some of SKF's areas. This talks about how we're committed to identify, engineer, and deliver world-class friction control and motion velocity control solutions to solve our customers' design challenges and needs. A little bit of history about Kaydon. Kaydon was established in 1941 by Harold Frunthal. Strategic growth. The interesting thing about Frunthal is he not only developed the company, we actually have some of the equipment, the grinders, he invented and developed himself in one of our plants down here. It's an interesting thing that the man not only came up with the idea for the bearings, but he also came up with the way to make them. So that was a cool thing. Talks about strategic growth and targeted business sectors, 12 business units serving a broad range of diverse markets. It's headquartered in Ann Arbor, Michigan. 21 worldwide manufacturing locations, 2,000 employees. Started producing large precision bearings for naval gun mounts is how it started. Kaydon. You're going to love this. The name Kaydon. Harold Frunthal had 2 kids. Kay and Don. I thought that was cool. Providing customers with problem-solving, application-specific, custom and standard pin section and slewing ring bearings. Slewing rings, very, very, very large bearings that we make. And this talks a little bit more. There's the different locations that are shown here. We actually have 2 plants down in Sumter, just a stone's throw from each other. We make bearings in Sumter here that they serve different markets: the medical, the semiconductor, the defense, industrial machinery, and aerospace. I brought some toys if you would like to pass them around and take a look at them because they're unique. A couple of them you're not going to pass around because they're pretty big. These larger bearings. Some of these are, if you really look at them, we're going to talk about the math in some of these things. They're neat. It's just amazing. When I started working there, I've been there now about 4 years. And I thought maybe I was going to find some bearings that I could use in my John Deere lawnmower. But they don't make that kind of bearing. That's actually a bearing. This is a bearing. That's an amazing little bearing. How we make it, I don't know. I'm supposed to run the place. This is about where we're at in South Carolina as far as the people and where a lot of the people come from that work at our plants, just to give you an idea of that. We're considered a world leader in thin section bearings, the North American leader in slewing ring bearings, specializing in thin section bearing slewing rings Experts in solving demanding bearing design requirements. Thin bearings save space and weight. Slow infinite bearings for optimal economy in a given envelope dimension. Some of those bearings that you have there, there's one that doesn't even look like a bearing. It's got a little arm sticking out of it. That goes in a semiconductor robot that's used to make silicon wafers. It's cool stuff. Some of the ones that are over here, I think the one is for a blood analyzer unit. In the medical industry, we make bearings for blood analyzers. We make them for CAT scan machines. We also, when we go to CAT scan machines, also go in luggage scanners that are used in the airports. It's kind of an amazing thing. We make bearings that are used from an application standpoint for military. Let me get a little farther into some of the things we do. Military applications. The large bearings are used on gun turrets. We make bearings that are over 12 foot in diameter. At one of our plants, we make them as small as 3/4 of an inch in ID for some applications as well. We make those that are used on helicopters. We use them. They're used in applications such as, let me see here. There's one of the large ones for you. Some of them that are used in aerospace, in planes themselves. That one's used in the steel mill. Amusement park rides, airline passenger bridges, satellite and radars. This is some of the ones, and more of them in Sumter that we use, are different positioning devices. Some of our bearings aren't used in rotational aspect. I always thought of the bearing just always rotating. Some of them are only oscillating and will move back and forth in such a way that it's used for extreme precision associated with things like telescopes, microscopes. This system is one that's used as an anti-missile system on planes. So that if a missile is fired, it's used to detect that missile, and it has to rotate in a heartbeat and move so that it can shoot a beam out and shoot it away so that the plane doesn't get hit. Cool stuff. Cool stuff. This again is in the semiconductor business that's used. A very precise, very accurate, has to be extremely accurate for what they do. This again is some of the analyzers that the larger bearings go into. The tanks that they go into from a turret standpoint, protecting people. A lot of neat applications, but we'll talk about the math and science in bearings. There's a lot of stuff that goes into these bearings that you have to get in from an analysis standpoint and look at, design-wise. First bearing goes back, actually, pre-Da Vinci had come up with an aspect of a roller bearing, a ball bearing like that. The idea is, it actually probably predates that, the idea of just rolling mechanisms and how to help move things along is a bearing. And so that gives you an idea of a basic ball bearing. There are other kind of bearings, aren't there? There are roller bearings that have rollers. We don't make those here in Sumter. We only make ball bearings. The ball bearings we make go down to 1/8 of an inch ball size. The interesting thing is the majority, in fact, in our plants, all of these bearings are put together by hand. It's not automated. Because our volume, for one thing, is not that high, and because the accuracy has to be there that well. That's tight. The balls themselves, these bearings that you're looking at, the roundness of them, many of those are what are called Class 6 parts. Class 6 parts are Class 7 ABEC, require that the roundness be within 2/10,000ths of an inch, 0.0002. The ball size increments that we vary are in 1/10,000th of an inch. When we receive those, the tolerance on those balls we get from the supplier are in the 50 millionths range. It's amazing stuff. And the measurement of that stuff gets very hairy, as you can imagine. Trying to make sure we're getting that right. Some of the bearings that we do go between, I'm timed out. That's it. Windows is not jingling. What about that? This gets into a little bit of an aspect, it's in one of our catalogs associated with the application of a bearing onto a shaft. Whether you're getting into it and you're looking at the thrust forces, the radial forces, the axis of rotation, the moment, come up with the moment load associated with it, so you can determine what kind of bearing you need. We have engineers, product engineers, who work out in Muskegon, Michigan, who are responsible for talking directly with customers in their applications. The application may vary in size, but it also can vary in things like what kind of lubrication do you want? Some are very exotic types of lubrication that go in bearings. Do you want the bearing to be preloaded or to have clearance? Some of the parts actually have the bearings themselves, the races, the inner race, the outer race, and the ball. The ball is less than the difference between the inner and the outer, so there is clearance in it. It's meant to be that way for that application. Others, the ball is greater than that space, so it's tight. But that's because certain applications cannot have any extra movement in it at all. It's going to have a little bit more torque to it. It's going to be tight, but that's the way that's been prescribed, that they want that. This is some more of it. Ball bearings themselves are not just, and I thought a long time ago, well, the ball contacts the bottom of the path. They do on certain aspects. Those are called a C-type bearing. C being right down the middle, the centrous type. There's also over here at the far right, this is an angular contact bearing. Depending on the application you have, gives you the requirement for what you want. In a case like this, a C-type bearing is one, if you look at from a loading standpoint, is going to be one that has a lot of radial loading to it. The bearing itself is in part of one of the bearings. Your loading is going to be a lot more straight on like this. So it can handle that loading better. The load it's not going to take very well is if I have a thrust load against it. It's going to want to try to come apart. An angular bearing is made specifically for that kind of a thrust application, so that when you push one way, you're always staying in contact and it's not going to come apart. Now with it, if you push the wrong way, it will definitely come apart. There is a snap land to it that tries to hold it together, but it does have that ability. And then there's this wonderful thing. This is called an X-type bearing. An X-type bearing, the ball actually doesn't sit in the bottom of the pocket. It sits on two things, and this is called part of the Gothic arch that was created. That's made by way of what we call, our methodology for making bearings is through grinding. And what happens is we have these things that are very precise called diamond rolls. Another name for them is a crush roll dresser. They're made and they actually have diamonds embedded in them, and they are very expensive. And what happens is you take and you dress the grinding wheel, you bring it up against the grinding wheel, and the form takes shape right into it. You use that grinding wheel then to grind this. And this is a hardened steel. We make out of two different kinds of steels, 52-100 steel and 440 stainless steel. Stainless, of course, because it won't rust. 52-100 will have a preservative put on it or have some type of coating put on it to protect it. So these are the different kind of things. And this gets into all of these get into some very neat mathematical relationships. You can see up there it talks about contact angle. Contact angle is very important into the amount of load that it can be placed into. This actually has two contact angles, and those have to be in such a way that the inner race and outer race are to somewhat of a degree of matching for the part to run correctly. If those are off, if these contact angles are significantly different than these contact angles, the ball won't rotate correctly on it, and will give problems. Some other things. This is a picture I wanted to show you. This is an induction hardener, and that is a 6-foot barrier, if you can picture that. In induction, there's two different ways of hardening steel. You may know this, but I wanted to share. Through hardening is you take and you would put it in a furnace, and we have furnaces that get up to over 1,500, 1,600 degrees. And so you take a piece of steel and you put it in there, and we put it in for a specified time, we bring it out, and we quench it and drop it into oil. And by doing that, we take the hardness of this from about a 40 Rockwell C up to almost 60. It becomes very hard. Other ways of hardening is called induction hardening, another way. What this does is, rather than, on the bearing itself, rather than the entire bearing getting heat treated, only the inner part where the path where the balls are going to rotate is heat treated. It becomes harder. The outer part of that bearing is soft, but the inner part then allows the balls not to wear against that part. This is some neat stuff because this is electrical. It induces that heat through it and hardens it that way. Our induction hardener of this type was induction hardener 0001. The very first one that was made of this type for our application. The neat thing about it is you can picture as this comes around, one of the problems would be is you would end up with, as it meets, you could potentially have a soft spot. Because this thing is mechanically moving around to do it. But the way that this has been made, they were able to do it in such a way that it has no soft spot. It's a very neat stuff. This is a new lab we're excited about. This is a cleanliness monitoring lab. One of the things we get into with our customers is associated with how clean we make our bearings. And it's not, I'm one of those people, I need data. I like data, that's that science thing, I want, give me some evidence. So if it's dirty, how dirty is it? What does that mean? And for us, a lot of times it's been very subjective. Customers, and rightly so, they can say, well, it's got to be contaminated because it's rough and it doesn't feel smooth. Help me define, how smooth do you need it? How clean do you need it? Well, the neat thing about this system is there's actually two pieces to it. This piece here is used, and what happens is this glass lid is lifted up. There are two rubber glove areas right here. You stick your hands through, and you take it and you wash out the bearing completely. Down below it, it all filters down into a little filter right there about an inch to 2 inches in diameter. And you have to define how many times you rinse through it, and you go through all that. You capture that, you take that filter then, and you come over here, and this is a scanning microscope that can actually go in, and it can tell you what kind of particulates you have, whether you have metallic particulates, whether you have non-metallic, and how small they are down to less than 5 micron. Amazing stuff. And it's something that we're just getting into to advance our work because our customers are expecting that. Because one of the things we do is we have a clean room. Our clean room to work in there for some of these bearings, not all of our bearings, but for some of the applications like semiconductor, like the positioning devices that were used for high-aspect military applications. You have to go in there, you have to completely put on a whole white suit, the gloves, the mask, the hairnet, the whole thing. Because they say even a small piece of dander, of eyelash dander, can cause a semicon robot to hiccup in its movement. And if it does that, it destroys the silicon wafer. Neat stuff. Neat stuff in how we do that. Inside there, we have capability that we can do torque testing. And we have some elaborate torque testing equipment. I think I showed that up here. The evaluation we do from torque is not just the amount of torque, but we look at the min-max torque of it. We look at that graph up at the top. And the two graphs represent rotating it clockwise, rotating it counterclockwise, to see if we have any difference. We have the ability to look at that graph and to tell you if there's any problems with the bearing, if there's problems associated with contamination, if there's any issues associated with the way that it was made. One of the things is called chatter, if it's ground incorrectly. Making sure that it's done the best possible way. Do you see mathematical and scientific applications in all this? Because boy, I sure do. I sure do. And we've lived through it, and I like this. I like what we do. One of the things, too, I want to let you know, too, about our application is we can say that our bearings actually are out of this world. on the Mars rover has Kaydon Bear. So that's kind of a cool thing to look back on and see that. My friends, one of the things I want to convey to you is I appreciate the opportunity to come here tonight to tell you thank you for the job you do, for the importance of what you do, and for passing on to the next generation and the next generation what it is that it means to have, I'm a nerd. I like being a nerd. I don't know about you all. I like the fact of math and science and engineering and technology. Those things have served me well in my lifetime. It's served my family well. It's provided food on our table in a very nice house that we have. It's because of you all, because of what you've done. Not every student is going to get the opportunity to be an engineer, nor do they want to be. But it's important that every student knows that you care. That's the greatest thing any teacher can do, is just care. Any human being. That's what at times I'm afraid we're lacking right now in our world, is not enough caring people. We just need to care a little bit more. We need to help, because there's a lot of jobs. Within our planet, Kaydon, not everybody's an engineer. There are people who are machine operators. They're very smart people because of what they learned in school. Continue to help the people. We've got to make sure we're doing that. Okay? I'll turn that over to